Okay, so I'm going to record the meeting, so if anybody misses part of it, they'll have it. What I think, Sang-Young, can you hear us?
Yes, Professor.
Okay, I think what we'll do first is we'll go over the yesterday's exam. You all should have received your exam by now. I shared them with you.
Okay, yeah, I checked mine. Thank you.
Okay, very good. So let me just take control of this thing again. I'll share the screen. So I'm going to go over the exam. And this is being recorded, so anybody coming late, they can listen to it as well. So let's begin with problem number one. In problem number one, I give you the probability distribution. We recall, let's get out of red. You can tell I was grading exams this morning. The moment generating function for a discrete random variable is nothing more than e sub t x sub I, p of x sub I, over all possible values. So we have, in this case, xi starts with 0, so we have e to the 0t multiplied by 0.15. And then we have e to the 1t multiplied by 0.10. And then we have e to the 2t multiplied by 0.25. And then we have e to the 3t multiplied by 0.20. And we have e to the 4t multiplied by 0.30. And of course, this first term is just 0.15 because e to the 0 is 1. Okay, so here's m of t. So if we know that in order to find the expectation of variance using m of t, we need the first and second derivative. So, and we also remember that the derivative of e to the at, where a is a constant, is just a e to the at. So what do we get? We get the first derivative. Well, derivative of constant is 0, and we get 3 times 0.2. Hold on, something's wrong. I'm sorry. We get 1 times 0.1 is 0.1. And we get 2 times 0.25. And 3 times 0.2. And 4 times 0.3. And that gives us the first derivative with respect to t. And if we differentiate one more time, let's do the differentiation first. We have 0.1 e to the t plus 1 e to the 2t plus 1.8 e to the 3t plus 4.8 e to the 4t. So the differentiation is now out of the way. I have m prime of 0 is equal to e of x. And that just turns out to be what? 1.8, 2.4, correct? Is that what I got before you? 2.4. So we have the mean. Is 2.4. M double prime of 0 turns out to be, what was that, 7.7? And that's equal to e of x squared, the second moment. Therefore, the variance, which is e of x squared minus e of x quantity squared, that's just equal to 7.7 minus 2.4 quantity squared. And if you work that out, I did that somewhere, we got 1.94. Okay, that was the first question. Question number 2. You were given 20 questions. Each question has 4 choices, so the probability of guessing correctly is 1/4. Clearly, if there are 20 questions, each question is worth 5 points. And the student decides to guess. Let's let X equal to the number of correct questions that were answered. So the first question is, what's the probability that a student gets a 90? In order to get a 90, you have to get 18 questions correct. Okay, now it should be clear that this is a binomial distribution. I had 2 people work the problem out using the Poisson approximation, and I accepted it. But this is clearly a binomial distribution. That's how this problem should have been done. So this is just simply 20, choose 18. The number of successes, probability of success is 1/4 to the 18th times 3/4 squared. And by the way, if you work this out, I did, the answer is something like 1.56 times 10 to the minus 19th, which is effectively 0. And that's what you expect. If somebody's guessing on an exam, the probability that somebody's going to guess correctly and get a 90 is non-existent. Okay. The second question is, what's he scores? At least, at most a 90. Well, most of 90 means X is less than or equal to 18. That's equal to 1 minus the complement, which is 19 or 20. So this will be a 20, choose 19, 1/4 to the 19th, 3/4, minus 20, choose 20, 1/4 to the 20th. And this starts out to be 1 minus 20 times 3 over 4 to the 20th minus 1 over 4 to the 20th. And this is almost 1 if you work it out, by the way. Okay. Then the next part of this question is, I ask you to find the expected number, the expected point score. Well, the expected number, X stands for the number of questions that got right, that you expect to get right. We know that's N times P, which is 5 questions. Well, if each question is worth 5 points, that means the expected score is 25 points, if one guessed. Similarly, V of X is N times P times Q. So that would be 5 times, times 3/4, which is 15 over 4. So sigma is the square root of 15 over 2. And this is questions. So if you want to know it in terms of score, it's square root of 15 over 2 times 5, which, by the way, for those of you who like numbers, is about 9.68 points. Okay. I did accept if somebody did the problem by Poisson, since I didn't rule out that possibility. I didn't say you had to give me an exact answer here. What they did, of course, lambda just becomes N times P. And then the problem is the arithmetic is probably a little bit easier. And the answer will be a little different, as you'll discover. Okay. Question number 3. I'm telling you X and Y are independent, random variables. X has moment generating function. Where is it? 2/3 e to the t plus 1/3 raised to the 4th power. That's telling you, by the way, if you look up at the table, x is binomial with parameters p equal 2/3, n equal 4. Similarly, y was given its moment generating function was given as, what was it? Which one did I give here? I probably gave the Laplace. E to the 2, e to the t minus 1. That tells you y is Poisson with parameter lambda equal to 2. Now, since x and y are independent, did I call them x and y or x1 and x2? X and y. Z is x plus y. So the moment generating function for z, since x and y are independent, is the product of these moment generating functions. And that will just turn out to be 2/3 e to the t plus 1/3 to the 4th times e to the 2 e to the t minus 1. So there's your moment generating function for z. Then I asked, what's the probability that, where is it? That z is equal to 2. Or equivalently, x plus y equals 2. Now let's remember x is binomial, okay, and y is Poisson. Well, this can only have, I'm sorry, x plus y. In order for this to happen, it can happen with x is 0 and y is 2. And all these are mutually exclusive, or x is 1 and y is 1, or x is 2 and y is 2. However, you were told these are independent. Therefore, by independence, this is equal to the probability that x equals 0 times the probability that y equals 2, plus the probability that x equals 1 times the probability that y equals 1, plus the probability that x equals 2 times the probability that y equals 2. And let's remember that x is binomial, so this would be with parameters, x is binomial with parameters 4 and 2/3. So this is 4, choose 0, 2/3 to the 0, 1/3 to the 4. Poisson is a parameter with lambda equal to 2. So that's equal to 2 to the 2, e to the 2 over 2 factorial plus 4, choose 1, 2/3 to the 1, 1/3 cubed. That would be 2 to the 1, e to the 1 over 1 factorial plus 4, choose 2, 2/3 squared times 1/3 squared. And this would be, this is 2, so this, oh, I'm sorry, this is 0, right? In this last case, this typo. And this is 2 to the 0, e to the 0 over 0 factorial, which is 1. If you work this out, I forget what the answer is. You didn't really have to work it out. It was 0.07, 0.07012, I believe. And then I asked, what's e of xy? Now, what some of you did, which is rather unfortunate, is you you were actually took the moment generating function of the product, which is wrong, by the way, and then you try to compute the n prime of 0 and so on. The fact that these are independent tells you this is e of x times e of y. This is just n times p, and this is just lambda, and that just gives you 16/3 for the expected value. Okay, number 4. Suppose a weighted coin with the probability of obtaining a head on any toss is 0.6. What's the probability that a head will occur for the 6th time on the 10th toss? I think I called this number M in the text. I'm not sure. Okay. Well, in order for this to happen, you must get, in the first 9 tosses, you have to get 5 successes. I'd never remember the formula, by the way, even though it was given to you. And on the 10th toss, you get a success. So the probability that we want, well, that's easy. So look at the first 9 tosses. We want 5 successes. That's a straightforward binomial. And on the 6th toss, we want to get success. And that probability is 0.6. So this just turns out to be 9.5, 0.6 to the 6, 0.4 to the 4. And I believe if you work this out, this turns out to be 0.15019 or something like that. And of course, the expected value was just m over p, which is 6 over 0.6, which is 10. Okay. A key punch operator has a probability of making an error. This is number 5. Has a probability of making an error of 0.004. And let's suppose they require 500 keystrokes. Okay, actually, this is a binomial distribution, but I say using a Poisson distribution, well, lambda is therefore n times p. 0.004 times 500 is 2. So, of course, if we're going to use a Poisson distribution, so in this problem, this will just be 2 to the k e to the minus 2 over k factorial. So now let's answer the question. The probability of no errors. Well, if we let x be 2, that just gives us e to the minus 2. We let k be 2, and that's about 0.135. What's the probability that we have at least 2 errors? Well, the easy way to do this is by complementation. The complement is none or 1. So what does that give us? 1 minus. The first one was e to the minus 2. And if k is equal to 1, we get 2 e to the minus 2. And this gives you 1 minus 3 e to the minus 2, which is approximately 0.59399. Okay. Next problem is number 6. I tell you x is exponential, that's what I'm telling you, and I tell you the parameter is equal to, well, I didn't tell you, I gave you the CDF, okay, the parameter is 3, but okay. And I told you that f of x is equal to 3 e to the minus 3x for all x greater than 0 and 0 otherwise. This is clearly the exponential distribution. And then I ask various probabilities. Now, I want to remark that rather than do this problem 4 times, remember that f of x is just the integral, in this case, from 0 to x of 3e to the minus 3x. And remember, this means the probability that x is less than or equal to little x. And this just turns out to be 1 minus e to the minus 3x. And it turns out if you use this, the arithmetic is trivial. What do I mean? Well, in the first question, you're asked to find the probability that x is between 0 and 1. Well, if you did the integration, of course, it would just be this. But I want to remark, and it's trivial, by the way. I want to remark, though, this is just f of 1 minus f of 0. If you did the integration up above here, you don't need to do it again. So that gives me 1 minus e to the minus 3 minus 1 minus e to the 0 power. Of course, this is 0. So so the answer to this problem is just 1 minus e to the minus 3. And for those of you who like numerical answers, that's about 0.9502. Now B, the probability that x is greater than 1. Well, the probability x is greater than 1 is just equal to 1 minus the probability that x is less than 1, which we just did. So this is equal to 1 minus e to the minus 3, or e to the minus 3, which is equal to about 0.0498, whatever. By the way, of course, you could have done this. But it was much easier to realize it was a complement, which gives me e to the minus, with the minus sign here, e to the minus infinity plus e to the negative 3. This, of course, is 0, and this gives you e to the minus 3. Okay, now this last part here, what's the probability that x is between 1 and 2, given x is greater than 1.5? Well, there's a conditional probability. It's equal to the probability of the intersection that x is between 1 and 2 and greater than 1.5 is just simply 1.5 less than x less than 2 over the probability that x is greater than 1.5. Now, a couple of you actually did the integrations, which would work, but notice the denominator is 1 minus the probability that x is less than or equal to 1.5. So if I wanted to do this with the least amount of work, I would say this is f of 2 minus f of 1.5 over 1 minus f of 1.5. And now remember, f of x is equal to 1 minus e to the minus 3x. So this gives me 1 minus e to the minus 6 minus 1 minus, was it 3x? E to the, what do I get here? Was that 4.5? Is that what I got? Yeah. over 1 minus e to the minus 4.5. So that gives you e to the minus 4.5 minus e to the minus 6 over e to the minus 4.5. I would accept this as an answer. Some people rewrote this a little differently, and then they got an answer, whatever that was. I think the answer was something like 0.79, something or other. Okay. Next problem. I give you the random variable f of x is equal to kx cubed if x is between 0 and 1 and 0 elsewhere. And the first thing I do is ask you to find k. Well, we know from the normalization condition, the total area under the curve from minus infinity to infinity, in this case from 0 to 1, must be 1 gives me k over 4. That tells us k is equal to 4. So now we know f of x is equal to 4x cubed between 0 and 1, and everywhere else it's 0. And by the way, while I'm at it, let's find e of x. We need that. That's just the integral of x f of x. In this case, it's just the integral from 0 to 1 of x times 4x cubed dx, which is 4 times the integral from 0 to 1 of x to the 4th dx, or 4 x to the 5 over 5 from 0 to 1, and that's just 4/5. Okay, so now let's look at the change of variable part. I said, let's suppose y is equal to minus 4x plus 1. By the way, that tells us 4x is 1 minus y, x is 1/4. Well, let's just write it this way. X is 1 minus y over 4. Therefore, dx dy, which we're going to need, is just minus 1/4. We want to find g of y, but we know from our theorem, since this is a decreasing function, we can apply the theorem. This is just equal to f of x times the absolute value of minus 1/4, or just 1/4 f of x. F of x is 4x cubed. So this is just x cubed. But let's remember, x is equal to 1 minus y over 4. And let's also note from here, when x is equal to 0, y is equal to 1. And when x is equal to 1, y is equal to -3. So this interval for g of y that's defined on is the interval between -3 and 1, and everywhere else it's 0. Okay, so that answers problem number 7. Problem number 8. Suppose you're told that a bus is going to arrive somewhere in this 1 hour interval between 3:30 and 4:30. So this is, let's do it in minutes to make our lives easier. This is a 60-minute interval. Okay. Which means the time the bus is going to arrive at any point on this interval is uniformly distributed. Now, some of you are working this out with formulas, but you really didn't need to do that. Because let me do B and C. Let me do B first. What's the probability that it arrives between 350, here's 350, and 4:15? How long is that interval? That interval is 25 minutes, right? Therefore, that probability of part B is just 25 minutes, since it's uniform, out of the 60 minutes, or just 5/12. Now let's go to A. What's the probability that the bus arrives exactly at 3:40? Well, here's 3:40. What's the width of that interval? It's a point. 0. Remember, for continuous distribution, the probability x equals a single value is 0. And the last part is, when is the bus expected to arrive? Well, we know that's at the midpoint of the interval. That's in 30 minutes, which means at 4 o'clock. Now, what some people did is they said, well, f of x is equal to 1 over 60 as we go from 0 to 60 minutes, and 0, of course, elsewhere. And then the probability that x is at 4 o'clock, whatever that is, whatever time I said, a, that's the integral from a to a of 1 over 60 dx, which of course is 0. But you didn't need to do that here. Okay. Suppose the grades on an examination are normally distributed with mean 75 and standard deviation 10. And the upper 5% get A's. What's the cutoff? Well, we'll first look at the standardized distribution. If the upper 5% get A's, then the remaining area is 95%. So the question is, what Z value is equal to 0.95? Well, if you look at the table, there are 3 possibilities. 1.64 gives you a Z value of, I forget, 1.65 is the same amount above. And it turns out exactly, so this is 0.95, this was 0.8995, say this was 0.9505. So this was right in between. So you could actually use any of these. Either of these from the table, or in your head, you could have gotten this one. We also know that x minus the mean divided by the standard deviation gives us the z-score. So the x-score is just 10 times the z-score plus 75. Well, depending on which one you use, if you use 16.4, or if you use 16.45, or if you use 16.5, on either case, you get one of these answers. What are my answers? 91.4, 91.45, or 91.50. I accepted any one of those answers. And the last question here was the following. It said, let's suppose x1 is normal distribution, normally distributed with, where I lost the place, 2, 1. And x2 is normally distributed with 4, 9. By the way, that means, of course, for this one, mu1 is 2, sigma squared is 1, mu2 is 4, sigma squared is 9. Okay, so I said x1 and x2 are independent. And I said, okay, and suppose I let x equal x1 plus x2. I want you to describe x. What kind of distribution is x? So here's what most people did. Not all. I'd say all but 5 or 6. They said, well, we know e of x is equal to e of x1 plus e of x2. So that's 2 plus 4, which is 6. And v of x, by independence, there is no covariance term here, is v of x1 plus v of x2, which is 1 plus 9, which is 10. And that's correct. But that doesn't tell me what kind of distribution. People then said, and it's normal. How do you know it's normal? It could be maybe it's another distribution that has mean 6 and variance 10. Now, the way to prove it's normal is the following. Remember, if you have n of mu sigma squared, it has PDF 1 over sigma. Oh, I'm sorry. I don't want to work at the PDF. I could. That's too much work. It has moment generating function e to the mu t plus sigma squared over 2 t squared. You got that right in the table I gave you. So if we look at the moment generating function for x1, what do we get? We get the mean is 2. The standard deviation, or sigma squared, is 4. And if we look at the moment generating function for the second random variable, which one was that? That was e to the 4t, and it was 9 over 2. Sigma squared was 9, is that right? I'm sorry, the first one had sigma squared equal to 1. This was a 1, right? Yeah. And we know, since they're independent, m of x of t is equal to the product of these two. And by laws of exponents, we just have to add the exponents. This tells us that this is a normal distribution with mean 6 and variance 10. So that's how we know, because the moment generating function uniquely determines the random variable. Okay, so that was your examination. Okay, anybody have any questions about any of this? I need to hear from you guys. How many of you are here now? What do we got? Okay, we got 5 of you. Okay, so now let's open to the floor to other kinds of questions. How did you guys have any questions about the central limit theorem? Some of the exercises I gave you there. Did I send you the solutions to the central limit theorem yet? I need somebody to talk to me. Will some people unmute themselves so I can talk to you?
Professor, sorry, I didn't get a chance to go over the central limit theorem. So
okay.
Maybe I work on over the weekend.
Did I send I worked out some examples. Did I send them to you yet?
Let me
Yeah,
check.
I think there was one.
I did about 10 problems in the central limit theorem in that last section. That was section 3.4. If not, I'll resend them. I'll send you guys a link. So does anybody have any questions on anything now?
Yeah, I have a question. So for the answers, do you expect us to like just type everything into calculator, or just have it in the form that we would put into calculator? Is that fine?
It depends. If you have time, I mean, there was plenty of time in this exam because I gave you almost a half-hour extra time. When I worked out the exam myself, first I did the problems, I worked them out, and then I went back at the end and I put in the answers. It's nice to have answers, but for example, if an answer, it turns out to be 1 minus e to the minus 5, I would accept that as an answer. But if there's time at the end, it's easy enough with the calculator to figure that out, isn't it?
Yeah.
Okay. So I guess I answered your question. Anybody else have any other questions about anything? Okay. Then I will make sure I resend the work solutions to the central limit theorem. If you have a problem over the weekend, you send me an email. I can't guarantee I'll get to it. I got a lot of things on my plate this weekend, but I'll try, and then I'll just send it back. Anybody else have any last minute questions? Okay, so Monday is our final. I'm going to start the final a little earlier. I'll probably start it at 10:15 in case you need extra time. I can't run it late because other people may have another exam at 12:30 or 1 o'clock or whatever it is. The exam runs until 12:30. It's scheduled from 10:30 to 12:30. I'll start it at 10:15. Any other questions? Okay, so I'm going to, I guess we'll leave now unless anybody has a last minute thing they want to say. Let me stop the recording.